All right, sorry about that. So we found the eigenvalues that were repeated. We found the first eigenvector. Now we're finding the generalized eigenvector. So that's the equation we're going to use for the generalized eigenvector. And once we find that second vector, that generalized eigenvector, we'll have to form our second solution using that other formula, right? Remember that one was the generalized eigenvector times e to the lambda t plus our first eigenvector te to the lambda t. So all that stuff together was solution number 2. All right, so let's go through this process now. That a minus lambda I, in that case, is just the same thing I had before, 0, 2, 0, 0. The only real difference is I'm not augmenting with 0 now. Now I'm augmenting with that first eigenvector. And now I would do the row reduction from here. Once again, we're in a pretty simple system, so I really don't have to do any real row reduction. I can just write out the equation. I have 2x2 is equal to 1. Once again, x1 is free. If I think of what this generalized eigenvector could be then, if x1 is 1, for instance, what's x2? X2 is 1/2 here. Now for my first eigenvector, that eigenvector is 1, 0. And any multiple of that eigenvector is also an eigenvector. You can write down 2, 0, 4, 0. This generalized eigenvector, could I take 2 times this guy and use that instead? I cannot. Remember, the generalized eigenvector is different than the eigenvector, right? I have to solve this non-homogeneous system over here to find that generalized eigenvector, because I can't just scale this. I could have other values here for this generalized eigenvector. I could have 2, 1/2, 3, 1/2, any value for that free variable. But the thing is, I'm not really factoring out that free variable. x2 is a fixed value. I can't change that. That one has to stay at 1/2. Okay? All right, so now I got x2. That means my second solution is going to look like 1, 1/2 e to the 2t plus 1, 0 t e to the 2t. And then my final solution for the whole system is c1 times u1 plus c2 times all of u2 like that. All right, questions? All right, just a quick reminder. I know it's last day, but can we still have our phones put away off of the desk? The bright side is, other than the final, I'm never going to harass you about your phones again. See? That should make you happy. All right, any questions about this solution, general solution here? All right. Plan for today, administrative notes here. I have caught up on my notes. They're all now on Canvas. All the videos should be on the YouTube playlist. I posted an exam review from a previous semester. It's Y's and X's instead of X's and T's, but the questions are all pretty much the same. I'll post a solution of that later today. So that's all available now. Today we're going to talk about the graphical representation of systems. We started that a little bit last time. We're going to finish it. And then I have a big kind of exam review that we're just going to walk through for today. Any questions? All right, one other administrative note. Turning the systems quiz. We said if eigenvector was 1, 2, right? Any multiple of that is also an eigenvector. That's also an eigenvector. We're good. If you had -1, 2 as your eigenvector, -2, 4 is also an eigenvector. Looks like my graders are pretty good at understanding that. However, they didn't seem to recognize that this is also just a multiple of an eigenvector. So it looks like they didn't catch that. They might have taken a point off for that. So far, about 4 people came up right after they saw that, had the same issue. So check your quiz. If you lost a point because It looks like a sign mistake, which really isn't a sign mistake. It's just a multiple of an eigenvector. After class, just come up here. I'll give you that point back. All right. All right, I had the first section solve this one. Kind of took up a little too much time, so I'm going to shortcut this. Here is your system to solve, but I'm going to tell you in advance that the eigenvalues are -1 and 4, and the associated eigenvectors are 1, -1, and 2, 3. So if I told you all that stuff, form the general solution. It's kind of a nice question this way because you'll probably have a question on the Scantron version that will look like this. It's assessing a very specific part of the solution process. So if I said, here's the system, I've done the hard work and calculated the eigenvalues, eigenvectors for you, how would you form the general solution? All right. So our general solution here is going to look like a constant times our first eigenvector, e to the first eigenvalue times t, plus c2 times our second eigenvector, e to the second eigenvalue times t. Right? That's just the general form for this nice distinct eigenvalue. All right, but now I want to look a little bit deeper at that solution. We talked last time about how really, if we simplify this, our solution will look like one kind of vector function with a big function of t in here, a big function of t. And so that if I looked at u of 1 and evaluated that, I would get an answer like 1, 2. And I could look at u of 2 and I might get some other point, 2, 3, or whatever it's going to be, right? Some other point value. And so for every value of t, I'm essentially getting a point value in return. And we can represent this as a system of parametric equations. So I can really represent u of t as some sort of curve here in two space. Okay? All right. Now I want to think about what specific curves we're looking at. So what I'm going to do is I have a big family of solutions here. This is a solution, which is a different curve for every value of C1 and C2. So let's just look at some important values of C1 and C2 and see what specific curves we get. So I'm going to say if C1 is equal to 1 and C2 is equal to 0, what solution do you get then? Go ahead and write down this solution. C1 is 1, C2 is 0. What does your solution look like? I think it looks like that. Okay. All right, now I want to plot this guy and see what this thing looks like. Well, the idea is when I'm looking at this, I am seeing a vector. I'm seeing a vector 1, -1 times some number. Right? If you put a specific value of t here, all you're doing is multiplying that vector by a number. But graphically, what does it mean to multiply a vector times a number? If you take a vector and multiply by 2, what are we doing to that vector? Scaling it. We're just stretching it. We're doubling its length, but it's pointing in the same direction. So I could say if t is equal to 0, I would have the vector 1, -1, over 1, down 1. I would have this vector, right? That point is on my solution curve. Right? That point here would be on my solution curve right here. Okay? But if I looked at other t values, I'm just scaling that vector. So instead of that vector, now I have one that's longer, or a little bit longer, or a little bit longer, or a little bit shorter. So really this line is that solution curve. Okay? Now the one other thing to note here is the parametric equation, which means I'm actually traveling along this curve with a specific speed and direction. So the question is, am I going away from the origin or am I moving to the origin for this one? What happens as t increases? What do you think? Towards or away? Towards the origin. How can we see that? Well, if t equals 0, we set them right here. If t equals 0, I get 1 negative. What about t equals 1? Well, then I would get 1 negative 1 times e to the negative 1, which is just 1 over e. E is 2.71 something, something, something. I'm going to be sloppy. I'm going to call it 3, right? In that case, it looks like this vector times 1/3, which would give me the vector 1/3, negative 1/3. 1/3, negative 1/3 is right about here. If t is 2, what am I going to get? I'm going to get 1 negative 1 times 1 over e squared. That's going to be even smaller. So as t increases, I get closer and closer to the origin. If I put in negative t values, I'd be out here. So the direction I am traveling along this curve is like that. Okay. Any questions there? Let's look at another specific curve. And this one I'm going to do real quick. If C2 was still equal to 0, but C1 was equal to negative 1, if I multiply a vector by negative, all I'm doing is flipping it, right? So all I'm going to do is get this curve on the other side of the origin, and that one will also be walking towards the origin. Okay. All right. Now, when I see that line there, I see that eigenspace. What are my eigenvectors? Or any multiple of 1, negative 1. That line represents all the multiples of 1, negative 1. Okay. So I can just plot those solutions by looking at the eigenvector and basically plotting the eigenvectors. Okay? All right, let's look at another one. What about if C1 was equal to 0 and C2 was equal to 1? Well, then my solution just looks like 2, 3, e to the 4t. That's going to look like the vector 2, 3, that vector, times some number. It's just going to be a scaling of that vector, so it's going to be this line. If C2 is negative 1, it would be this line. But once again, I see that as just all the multiples of the eigenvectors. And then the next question would be, which way am I traveling along this curve? Which way am I traveling? Towards or away from the origin? Away. What's the value that tells you that? The 4t, right? Because that eigenvalue is positive, I'm going to be traveling away from the origin here. Okay? All right, so I got a couple solutions here. I've so far plotted 4 solutions. What about all the rest of them, right? Well, if we look at one more case, if C1 was equal to 1 and C2 is equal to 1, well, then I basically get something that looks like this thing without the C's. And I want to say, well, what happens as t gets big? Well, as t gets big, the left term, 1 negative 1 e to the negative t, that's going to get smaller and smaller. That's going to be a transient term in the system. It's going to go away as t gets big, because that means negative t. So the bigger the t value, the more my solution is going to look like that vector. The closer it's going to get towards that family of eigenvectors. The bigger it gets negative, if I put big negative values, now this right-hand term is going to go away. But this left-hand term will get bigger and bigger. Okay? So I can imagine if I put a very big negative t value, let's say if I put t equals negative 100. My solution would basically look like 1 negative 1 times something really, really big, plus 2, 3 times something really small. It's pretty much going to look like that thing stretched out. It's going to look like something way over here. Oh, that was a negative. Way over there. Okay. And then if t increases, this thing is going to get smaller and smaller. This thing is going to get bigger and bigger. I'm going to end up way over here. What's going to happen for t values in between? My solution is going to go like this. It's going to come in here. I'm going to go in that direction. Okay. So the idea is, when I see my solution form like this, I can sketch out all of the family of solutions by just drawing my eigenvectors, figuring out which direction I'm traveling along them, and then following the flow lines in between. That's going to go like this. These ones are going to go like this. That's going to go like this. And now I can really visualize all of the solutions here. Okay. Any questions there? All right, let's take a look at this for real. Here I have Mathematica open. I got 1, 2. Let's change this to 3 and 2. All I'm going to do is define that matrix, and now I'm going to look at the vector plot for that guy. Okay. Of course, my sketch was pretty sloppy, but can you see all that action here? Right? I can see if I'm looking for straight line solutions, I have one here. I have one there. I have one here. They're both traveling that eigenvector direction. They're both traveling towards the origin. I see kind of there's going to be a straight line solution somewhere in here, somewhere in here. I can see all my solutions kind of flow in those directions. Any questions there? Okay, we look kind of at one case here. The idea is for distinct roots. I get these two distinct terms. I get these beautiful eigenvectors. If I want to sketch that, I just plot those eigenvectors. Boom, I'm done. Because I can see each one of those solutions is basically some scaling of a vector. However, we think more generally, and what we could get in any system, we basically have these three cases. I could have distinct eigenvalues and get solutions that look like this. Now I kind of know how to plot those. But what if I get repeated eigenvalues and my solution looks like this? Well, here I see one scaling of an eigenvector, but this is not a scaling of an eigenvector, right? Because I have this extra factor of t in here. It's going to add some sort of curve to my system. So I'm going to have a different looking plot from there. Let's see what one of those guys look like. If I go like this, and I show you what the eigen system is. Oops, that's not right. There we go. I have a repeated eigenvalue here, so I'm in that case. Look at my eigenvectors. I have an eigenvector that's 1, 0. What's going on with that 0, 0 thing? Is 0, 0 an eigenvector? Can 0, 0 be an eigenvector? No, we're looking for non-zero vectors, right? That's a 0 vector. Why is Mathematica telling me this? Because there is only one eigenvector. It's 1, 0. In this case, I'd have to do that generalized eigenvector to get that thing. But now if we look at the vector plot, I get this thing. What am I seeing here? I'm seeing that one eigenvector. I'm seeing the eigenvector 1, 0. That's my straight line solution right here. 1, 0 or negative 1, 0, because any multiple, right? But I'm not seeing any other straight line solution. I'm seeing this curving action. That's because that other eigenvector is hidden in that more complicated second solution. Any questions there? Without even knowing what this system looked like, if you said the system has this vector plot, I can tell you what the one eigenvector is, and I can tell you that we're in the repeated root case. Okay? Those are things we want to be able to take away from the vector plot. And then lastly, look at this system. If we have complex roots, this looks ugly, right? It's like C1 plus a bunch of junk with sines and cosines and other weird vectors. Over here it'd be the same thing, ugly stuff, sines, cosines. In neither solution am I going to see eigenvector scaled. So am I going to expect to see any straight line solutions in that direction field? I'm not. So let's take a look at that guy. I can generate that by putting a -2 here. You see I have my complex eigenvalues and eigenvectors, so my solution would have that complex form. And what's the system going to look like? No straight line solutions. It's a swirling direction field. Okay? So the forms of those solution types can kind of explain what their fields look like. Now, what do I need you to be able to do? I need you to be able to say, hey, here are 3 fields. Which one is associated with a distinct eigenvalues case? Right? You say, that's the second one. Yay! Right? I know that because I can really see eigenvector here, a straight line solution, and probably somewhere in there. I can kind of see that there's two straight line solutions. So I can see that this is a case where I'll distinct eigenvalues. What about this one? Repeated or complex? Repeated. Repeated or complex? Wonderful. That's all I need. Any questions there? And really, if I wanted, I could do more. I could look at this system and say, not only is that thing distinct eigenvalues, but one of those eigenvectors is probably going to be, let's see, if I went over a half, maybe went up 3/4. So if I went over a half, I'd go up 3/4. That's probably an approximation for the eigenvector. Like I could really get a numerical approximation for the eigenvectors by looking at those solutions. Okay. I wouldn't know the scaling of the exponential very well, but I could get a sense of the eigenvectors. All right. That's really all I got for systems. Any last questions about systems? All right. I'm going to print these notes, post them after class, so I don't want you to be looking at a spot like this and saying, I'm going to write all that stuff down, because we got a half an hour to review the whole course. So I'm going to go quick, right? So you're not going to have time to copy all these highlights. I really want to talk through them and have you do a couple sample problems, kind of remind you of what we covered, and maybe highlight what your strengths or weaknesses might be. That's the kind of the goal of the quick review. All right. And the other goal is just, kind of like when Facebook hits you up with something you did a year ago and you're like, oh, look at that memory. It's kind of like that, right? We're going to take a little journey, a little look back through the course, the fond memories you have from differential equations, right? I don't know. Maybe it's more like a survivor walk, I guess, at the end, right? Always the worst episode. All right. Chapter 1, what are differential equations? We talked about classifying them. That's the big one, right? Make sure you review that classification because those should be the 3 points, right? By now you should be strong at, is it a first order or a second order? Is it linear or nonlinear? Those are the points you want to make sure you get. So classification is important. Why do we classify? Because depending on the group, we might apply a certain technique. We talked about existence theorems. So if you have a differential equation that looks like this, I want to know everywhere there exists a unique solution, I have to check that right-hand side, find out where those things are well-defined and continuous, and also the partial of f with respect to the dependent variable. Those are the two things I had to check. So for instance, here's a differential equation. Go ahead and classify it by order, linearity, and autonomy. And the next question is, does there exist a unique solution through this point and through the other point? Let's go ahead and see if you can answer these here. And remember, this is not a quiz. This is a review. All right, what's the order? First order, linear or nonlinear? Nonlinear. Which variable are you checking for that? X, right? That's the guy you're looking at here. What about autonomous? Autonomous or non-autonomous? Non-autonomous. Why? Looking for that t, right? There is an independent variable on the right-hand side. Awesome. Does there exist a solution at 0, 3? Let's start with existence first. Does there exist a solution there? There does not. This is my t value. This is my x value in this case here. So I'm checking the square root of x over t at the point where t equals 0 and x equals 3. I can't put t equals 0 in here. So there does not exist a solution because t can't equal 0. Does there exist a solution here? Well, if I put that in here, I'll get square root of 0 over 1. That's 0. Yes, there does exist a solution that goes to that point. Is it unique? Well, let's check the partial. The partial of f with respect to x is 1/2 x to the negative 1/2 over t, which I can simplify to be 1 over 2t square root of x in the denominator. Now can I plug in t equals 1, x equals 0? I cannot, because the partial is not defined at that point. There does exist a solution, but it's not unique. It's not unique. Any questions on existence and uniqueness? All right. Now we talk about solving first order differential equations. We want to solve them graphically, analytically, and numerically. So we looked at our graphical solutions. We want to talk about direction fields and autonomous differential equations. What are equilibrium solutions? All that kind of good stuff. I got 3 differential equations here. Which one is autonomous? C is autonomous, right? First one, I'm checking, are there x's in the right-hand side? Yes, there are. Are there t's in the right-hand side? Yes, there are. Are there t's in the right-hand side? No, they're not. This is the autonomous one. It's autonomous and might have equilibrium solutions. Remember, equilibriums are solutions that look like z equals some constant, right? These are straight line solutions that look like this. What is the slope of that straight line solution? 0. It's flat. It's a straight line here. Straight horizontal line. If the slope is 0, I'm looking for when this guy is equal to 0. That will tell me where those equilibrium solutions are. So in this case, I have 2z minus z squared, which factors into z times 2 minus z. So when is the slope equal to 0? When z is equal to what and what? 0 and 2. Those are my 2 equilibrium solutions. Okay. Those are my equilibrium solutions. So I should be able to look at a differential equation and determine if it's autonomous and where its equilibrium solutions are. I should also be able to look at a graph and determine if it's autonomous or non-autonomous and where its equilibrium solutions are. Which one is autonomous? A is autonomous. Why? Because the slope here is one thing, but if I just change the independent variable, over here I get a different slope. Same thing here. Negative slope, positive slope. But I only change the independent variable. Here, slope, no matter where I travel horizontally, same slope. That's autonomous. The equilibrium solution is what? -2. Right? Somewhere in there's a horizontal solution. Okay? Any questions here? Is that equilibrium solution stable, semi-stable, or unstable? Unstable, because all my neighboring solutions are traveling away. Really what that means is if I have a little change in my initial condition, one solution will go like that, and the other solution will go like that. It'll cause big problems later on. Is really what that means. We can see that if solutions are going away versus towards. All right, then we had a bunch of solution techniques. We had to solve the differential equations analytically, either with separation of variables, the linear method, or exact equations. I'm going to do separation of variables real quick because I think that's the easiest technique and the one we want to spend the least amount of time on. So I'm going to zip through this one, okay? What am I going to do? I'm going to separate the variables. I'm going to divide through by x, multiply through by dt. I'm going to integrate both sides. I'm going to get the natural log of x over here, t squared over 2. Don't forget your constant. Right then, take the exponential of both sides. I'll get t squared over 2 plus c1. I'm going to use my exponent properties to rewrite this like this. That looks like my good solution. All right, so x is equal to c2 e to the t squared over 2. That's a 2. Now I want to evaluate my initial condition here. That tells me that x is 4 when t is 0. E to the 0 is 1, so it looks like my constant is 4. And my solution is 4 e to the t squared over 2. I know that's fast. Any questions, though? All right, fast because I'd rather spend more time here. Okay, so this one I want to give you some time to work through. Linear technique. I wrote down my steps. Hopefully that jogs the memory and you can get through it. Start at a couple of steps. And the first step is important, but it's standard form is dividing through by that leading coefficient. And start by dividing through by t. Remember, the point here is to help guide your preparation. That's not where it's very probably like, wow, I lost some money at the beginning and I don't know what to do. You gotta go work your separation variables. You zip through this problem, it's no problem at all, and you focus your attention somewhere else. You probably won't have time to write down all those steps that I'm writing. Those are in your notes somewhere else. I'll send a PDF of this afterward. Let's see if you can get through that solution process. All right, there's my integrating factor. I'd use a log property here. The next step is not really necessary. You can multiply your equation by t, or by your integrating factor, sorry. By your integrating factor. This is really the process where it comes from. Then we then recognize that left-hand side as the derivative of your dependent variable times your integrating factor, which is equal to your function, f of t, times your integrating factor. You can really jump to this step. That's okay. And remember, we said one of the stresses was there are two ways we solve differential equations. We either manipulate the equation so that we can straight integrate it, or we make a good guess and find our missing parameters. Here we've multiplied through by a special function to simplify this thing so we can straight integrate it. And that's what we do now, we integrate. I integrate both sides with respect to t to get this. Don't forget your constant. And then I divide through by t cubed. All right, questions? Yep. How did I get here? This one right here? All right, so the idea was, I know this is going to happen, right? So the question is, why is this thing equal to this thing, really, right? What? Right here? I'm sorry, we're here. Very first equation. So to get to this equation here, t to the fourth over here. Okay, so I took my whole equation, I took this equation, and I multiplied it through by my integrating factor. So I multiply the whole left-hand side, and I get t times t to the third. Might take me a while to catch on, all right? But make sure you ask your questions. You want to get your questions answered, all right? It's going to be your grade on the final. So any questions you have, somebody else is going to have the same question. Other questions? All right, any questions for linear? All right, the next one, exact equations. Oh, our next Facebook memory. See? Exact equations, good old exact equations. I remember the core concept of exact equations was really a Calc 3 idea. It really says that what if we have some function of more than one variable? Right? What if we have this guy? I want to figure out how this function changes. Well, I can't just take the derivative because I have two variables here. So what does it mean to find out how does that function change? Well, to do that, we say let's take the partial of that function with respect to x times dx, plus the partial of that function times with respect to y times dy. Okay, that's the differential. You might have seen this in Calc 3. And then we say, well, wait a second, what if we look at a special function that's just equal to a constant? Well, if it's equal to a constant, it's a flat surface in 3 space, then how does that function height change? It doesn't. So if that's true, then df is 0. Okay? And so with that thought process, we say, okay, if we run into a differential equation that has that form, this could be a solution, right? And so that's kind of the situation we're in. We're hoping that this guy is the partial of some function with respect to x. We're hoping this piece is the partial of some function with respect to y. The only reason that's true, or one way we can show that that would be true, that there actually is some function f that makes that true, is that their mixed partials are equal. So what do we do to check to see if the equation is exact? We calculate this thing. That means I take the partial of this piece with respect to y. I get a value of 1 here. Then I check the other mixed partial, the partial of this thing with respect to x. I also get 1. So it is exact. So that means this piece really is the partial with respect to x of something. This piece really is the partial with respect to y of something. And all I want to do is find out what that function is so I can form my solution. All right, so what do? I integrate f of x with respect to x. I get x squared plus y times x plus some constant. No, I'm doing a partial integration with respect to x. That means this thing could actually be more than just a constant. In fact, it could be any function of y. That's where we added our little psi y of guy. Psi y guy. All right, now how do I figure out what psi is? So this is basically my solution. That's my f guy, right? But I don't know what the missing piece is. To figure out what that is, I calculate the partial of this thing with respect to y. Like this is my first guess at f. I take that guess and calculate this. I get 0 plus x plus psi prime. That's one representation for the partial of f with respect to y. But wait a second, I have another one up here. This is also supposed to be the partial with respect to y. So I can set those things equal to each other and solve for psi prime. Looks like psi prime should be 6y. It better be just a function of y. If it's not, I made a mistake. Now I can find out what psi is by integration. Psi must be 3y squared. So it looks like my function is x squared plus y times x plus 3y squared. Is this my solution? No. That's what my function is. My solution is x squared plus y times x plus 3y squared equals constant. My solution is f of xy equals c. This is my solution. All right. Now there was that dirty little secret, right? The dirty little secret was that we could really take our equation where we said this was f sub x and this was f sub y. We could really integrate f sub x with respect to x to get x squared plus y times x. We could really integrate f sub y with respect to y to get xy plus 3y squared. We can't just combine them. They both have the same term, and we can only use that once. But we really can then write this as that thing equals constant. Okay? That seems much easier, right? Why don't we just do that every time? Well, the reason is because that is more useful and more quicker for solving this kind of differential equation. The reality is just solving a differential equation isn't all that useful. We have that right? But that process is something you'll see in other courses. Like PEs, some other courses where you have to put that generalized sign line there. So that process is something that's important. You know, use a more complicated courses. Right? So it's good for you to do that. Okay? If you're on the exam and you solve this equation, you're certainly welcome to use that other technique. Okay? Just make sure you don't double count that xy. Don't add them together and write 2xy, because that would be wrong. Okay? Any questions there? All right. And we had numerical techniques. We had Euler's method to solve these differential equations. And remember, we had this graphical interpretation for Euler's. Euler says we have some starting point at 1, 2. And all I know at that point is what the slope is. I can say, well, if t is 1 and x is 2, the slope there must be equal to 3. So I know that if I'm at this point, I'm traveling in that direction. And I could follow that from some little time and find the next point, and then calculate a new slope and follow that to find the next point. That's the idea behind Euler's. Now, probably the easiest way to actually calculate all those different points along the way is to build your little table. So I have my starting point. I'm starting at the point 1, 2. I'm going to calculate my slope, which is this, in this case, is equal to t plus x. In this case, the slope is 3. I'm going to take some little step in the t direction. Sometimes we call this h as a step size. This is something I choose or is told to me in the problem. If I'm going from t equals 1 to t equals 2, and I'm using 2 steps to do it, what is my step size? 1/2, right? It is 2 minus 1 divided by 2. It is your final t value minus your first t value divided by the number of steps. If my slope is 3 and I travel a step of 1/2, what is my change in x? My change of x should be my slope times my delta t. Why? Because what is slope? Well, slope is the rise over the run. Right? So in this case, this would be 3/2. If my last t value was 1 and I changed it by 1/2, my next one should be 3/2. If my last x value was 2 and I changed it by 3/2, my next one should be 3.5, right? Or 7/2. And then we repeat the process. Here I will have 10/2 or 5. This stays the same. This goes to 5/2. This goes to 2 and 12/2, which is 6. So x of 2 is approximately 6. Any question about Eulers? It's a flow thing, right? Get good at practicing building your table. All right. And there we went on to high order differential equations. This tends to be a kind of a recent thing, and the first part tends to be one of the easier topics. First, before we got into that, we had some theory. The big idea was the solutions to the homogeneous differential equation, not the inhomogeneous, but the solutions to the homogeneous differential equation formed a vector space. And that led us to kind of do all that theory stuff. Some of the things we had to do along the way, we had tests for linearly independent, so we did a Wronskian to check for that. But really the big idea was, how do we solve homogeneous equations? Right, to do that, we generated our auxiliary equation. We found the roots and we formed our solutions. So make sure you review those different solution forms. You know what to do if you get complex roots or repeated roots, and you form those solutions. Then we did undetermined coefficients. We did variation of parameters. So remind yourselves of those techniques. And then the thing we're most fresh on would be systems. All right. Final exam is in Fisher 135, Thursday at 3 p.m. I will be in my office most of the week. I will try to arrange a few optional review sessions. I'll send you some time information about that. Send me emails. Stop by and visit my office. And good luck.